I'm Bill. I've been working in storage development for 28 years. I've spent the last 6 months looking at Ceph, and I want to share with you today my kind of thoughts and visions on how we can improve Erasure coding. And so today with Ceph, if you're storing objects, then you're probably using Erasure coded pools. If you're using block or file, then you're probably using replicated pools. And the reason for this is performance. When you're doing small random access to Erasure coded pools, you don't get the kind of performance you want, and so you end up using replicated storage pools instead. That's great for the performance, but obviously having a replica 3 pool means you've got a lot of storage overheads. You've got 3 times as much physical storage as the amount of data that you're storing on your cluster. So, the attraction of Erasure coding is a lower total cost of ownership. You need less physical storage for the amount of data you're storing. So my vision is, how can we make Erasure coding give similar performance to replicated pools so that we can use it for block storage and file storage. Now, you're never going to get as good a performance as with replicated storage. The objective here is to make it nearly as good enough so that you can use it, and the very slight difference in performance, you can trade that off for the lower cost you get from being able to exploit Erasure coded pools. What are the performance bottlenecks we need to look at here? So bandwidth, typically these days that's limited by the network connections between your Ceph nodes. IOs per second, IOPS, with HDD storage, you might be limited by the performance of the HDDs. If you've got modern NVMe drives, you've seen the performance figures that have been shown today. A Ceph cluster probably isn't able to drive a large number of NVMe devices flat out. What's actually going to limit your performance is the amount of CPU power you've got, and so you're going to run out of CPU before you actually manage to saturate the NVMe drives. The other thing, and this is what end users probably really care about when you talk about performance, is latency. And so this is, how much delay is there in reading and writing the data? And that's the performance measurement that applications are sensitive to. When the latency creeps up, that's when the applications become sluggish. That's when your end users start complaining and shouting and saying, what's the storage doing? Why is my application so slow? Okay, so let's start by looking at reads. So here's what happens today with a read. So the Rados client issues a read to the primary OSD. It actually goes and reads data from all of the data OSDs in the Erasure coded pool. Even if you're just reading 4K, it'll still go and read from all of them, discards all of the data it doesn't need, and then sends the data that is actually requested back to the client. So we don't need to be a rocket scientist here to say, how could we improve this? Looking at this chart, at the top there, the transfer to the Rados client, that's obviously using network bandwidth. So we're interested in how much data is being sent there. The OSDs, storing the data, those are probably in different servers for reliability reasons. And so you're consuming network bandwidth as you transfer data between the OSDs. And so the more arrows we see at the bottom here, the more network bandwidth we're consuming, the more that's going to have impact on bandwidth. The number of accesses to the OSDs, that's the other thing we need to consider. If you're using HDDs, then the more accesses you have there, the more that's going to limit your performance. If you've got all NVMe storage, then the more accesses you have there, the more CPU time you're essentially using up. And so the more arrows we see on these diagrams, the more that's going to be affecting your performance. So less arrows is better. So, as I said, don't need to be a rocket scientist to say how can we optimize this. And so a partial read is where the client issues the read, and rather than going and reading all of the data drives, we only actually go and read the one that's got the data that we need on it, and then we send that data back to the client. So we can see a lot less arrows, so saves a lot of network bandwidth, less CPU overheads, less number of IOs. This has actually just been delivered upstream into main. So this will be coming to a Ceph release soon. I'm not sure whether it's going to be backported to Squid or not, but certainly will come out in the T release. So this is the first optimization, clearly going to help read performance. We should look at some of the error paths as well. So what happens if the initial read fails? So you get an IO failure reading from drive 3. So what will happen then is we'll then have to go and read the other data drives and one of the coding parities to actually be able to go and reconstruct and recover the data. And so that's a second set of reads. So we do one read, that fails, we then go and do a second set of reads to get the other data needed to reconstruct and recover it. That's actually no worse than the current implementation. So the current implementation would have read data 1, 2, 3, and 4 all together to begin with. If data 3 failed, it would still have to then go and issue a second read to read the coding parity. So the partial read optimization, although we're reading less initially, might have to read more in an error recovery scenario, but it's still only 2 batches of reads. And so latency, how long does it take for the read to be served? That is going to be based on how many sets of reads we issue in series. And so one read of data 3, then a second set of reads of the others in parallel. That's 2 sets of reads, no worse than it is today. I should point out that we only do 2 sets of reads like this when the read failure is unexpected. So if data 3 was missing, then even with the partial reads, we'll straight away go and read all of the other datas and a coding parity to be able to recover the data. So if there's a known failure, then just one set of reads to recover the data there. How can we optimize it further? So you saw the read being a zigzag line, and that's because the client issues all of the read and write IOs to an Erasure coded pool to the primary OSD, and that might not actually be the one that stores the data for an Erasure coded pool, and so that then means the primary OSD had to issue the read IO to the OSD that actually had the data on it. With a replicated pool, you don't have that problem. If you issue the IO to the primary OSD, it's got a copy of the data. It can go and read its local copy. So with Erasure coded pools, what we want to do is change it so that the client understands which OSD's got the data on it, and it can send the read directly to the OSD that's got the data, and it can then return the data directly to the client. And so this avoids a hop between the OSDs, so it's saving network bandwidth, it's saving CPU time, because sending that data across a hop like that is got overheads, CPU overheads, sending and receiving the data, so that it's actually going to reduce the CPU overheads, and it's going to improve the latency as well. So actually just transferring data once across the network as opposed to 2 hops across the network is going to help lower latency. With this optimization, you should get the same read performance with Erasure coding that you get today with replicated pools. And so that would say, just those 2 optimizations, if you only had a read-only workload or a mainly read workload, this would make Erasure coding viable for block and file.
Can I ask? So
Yeah.
Is that not affecting the performance of the client?
The client's having to choose which OSD to send the I/O to, so there's a tiny bit of extra computation there in saying which one do I have to send it to. You've got to remember that you have many placement groups, and so the client is already sending different I/Os for different objects to different OSDs anyway. So the client's already sending and different I/Os to different OSDs. Now saying that you send I/Os directly to the OSD that's got the data.
How is the client's having to?
The client's got a little bit of extra computation. So it's a tiny amount of extra CPU overhead in the client to actually calculate which OSD it's got to send the data to. I mean, it's already running the crush rules to do the calculation. It's kind of a tiny extra overhead there. It's probably sub 1% CPU usage. So small overheads. What happens for larger reads? So for a large read, it may be that the data's not stored on just one OSD. So the client could split a larger read and issue reads directly to multiple OSDs, and they could then return the data. That is certainly the most efficient. There is a caveat here though. So if we issue 2 reads to 2 different OSDs like that, they're now separate I/O operations, and so they're no longer atomic. And so if you issue the read to the primary OSD and it then issues the reads to the other OSDs, it can actually block write I/Os from happening whilst those 2 reads occur. If we issue them directly like this, we're now saying a write I/O could actually sneak in between the 2 reads, and so you might actually be able to observe half a write when you read the data back. So some clients don't have a problem with that and can kind of cope with that, and so they can use this type of optimization. Some clients, and for specific tasks they're doing, they can't cope with that. They expect the atomicity that a read can't observe half a write, and so this optimization is going to have to be selective. For some of the kind of block use cases, I think we can get this optimization to work, at least for the kind of main stream cases, for the kind of 95% of the I/O. There might still be exception cases where we can't apply this optimization. Okay, so that was read I/Os. Now let's have a look at write I/Os. So what happens with a write? So this is the initial write of an object. So the data gets sent to the primary OSD. It actually calculates the coding parities, so that's a bit of CPU time to do that calculation. It splits the data up and it issues writes to each of the OSDs to store the data and also to store the parity codings. This is actually pretty efficient. There's not very much we can do to optimize this. And this is why when you're using Erasure coding with object storage, you actually get good performance. So S3 objects are immutable. They get written once, like this. They then don't see any overwrites. Typically, when you're reading S3 objects, that's long sequential reads of large objects. And so, the fact that you're reading all of the data drives doesn't matter because you're doing that large sequential read. When you've got block and file, the problem is that you need to deal with overwrites. And so data doesn't just get written, and a block device isn't immutable, a file isn't immutable. It gets written, and then you get kind of random overwrites occurring to the block device or to the middle of the file. The current implementation of overwrites is not particularly sophisticated. What it does is it reads all of the old data. It merges the new data that is being overwritten into what it's read, calculates the new parities, and then writes all of the data and the parities back out again. And so if you're just modifying 4K of data, it goes and reads everything, does the update, merges it, recalculates, writes everything back out again. So very inefficient, lots of arrows there, so we're burning lots of network bandwidth, we're burning a lot of CPU. That's essentially why short random overwrites to Erasure coded pools today gives you such terrible performance. There's some fairly simple optimizations we can do to this. So the first thing is it really does go and read all of the data. So if I was actually overwriting 95% of that data, it would still go and read all 100% of it, and then it would merge the 95% that we're overwriting with the 5% that it needed, calculate the new parities, and then it writes everything back. If I'm only modifying 5% of it, it reads 100%, merges the 5%, and then it writes all 100% back. I've only changed 5%, so why am I writing all of the unmodified stuff back again? So very simple optimization, only read the data that's not being modified, merge in the new data, so now I've got all of the data, I calculate the new parities, and then only write the modified data and the modified parities. And so you can see, with this optimization, I've essentially halved the amount of I/O I'm doing. All of these examples I'm showing here are with a 4+2 Erasure coding. I mean, obviously, I've chosen a fairly small sized Erasure coding just for the diagrams. The same technique applies for all of the Erasure coding configs. If I had something like a 8+2 config, yes, I've reduced the number of hours here, but that's still 10 drives, that's 10 IOs I've done to perform, say, a 4K update. So this is better, it's still not good enough. So the next technique we can use is called a parity delta write optimization. And this is very commonly implemented in storage controllers that have RAID 5 and RAID 6. But the same technique does actually work with Erasure coding and can be generalized to work with any Erasure coding. So how it works is we read the old data and the old coding parities. You XOR together the old data and the new data to perform a delta. And you then apply that delta to the coding parities, and that applying the delta to the coding parities is actually using exactly the same maths and the same algorithms that are used to generate the coding parities from scratch. And that actually produces the new coding parities for you. And so that says you can do a short update just by reading the old data and the old parities and then writing the new data and the new parities. So that for a +2 config is 6 I/O operations. Now the nice thing here is it doesn't matter about my Erasure coding config. If it was a 10+2 or a 20+2 Erasure coding, it's still 6 I/O operations. If I have a 4+2, 6 I/O operations there. If we actually went back to this simple optimization, you can see we've only got 6 I/O operations there. So actually with a 4 plus 2, there's very little benefit in the parity delta write. The fact that it's doing the read and write to the same OSD, there'll be a little bit of caching of metadata, and so it's probably fractionally more effective with 4 plus 2. If I went to a 3 plus 2, then the simple overwrite would actually be better. So, we need to be a bit smart about a parity delta write optimization, and we can actually calculate up front how many IOs is it going to involve. Is it better to try this technique, or is it better to just use the simple overwrite optimizations? And so simple calculation lets us choose what to do here. So we see, we're still sending the write IO to the primary OSD, and we've still got those kind of horizontal arrows, and so we're still consuming network bandwidth between the OSDs. One of the nice things with the parity delta write is we can actually start to distribute this process. So we can actually read the old data, XOR it with the new data on the primary OSD. That gives us the delta. We can send the delta across to the OSDs that have the coding parities, and then they can do a read of their parity, apply the delta, and write it back. And so still same number of IOs, but we're doing the read and write for the parities on the parity OSDs themselves. So the amount of network bandwidth we're using has been reduced. One issue with this is latency, because we have to read the old data, XOR it to generate the delta, then we send that across to the coding parity OSDs, and only then can they start doing the read of the old parity. And so this actually increases latency. The way to fix that is as soon as you receive the write IO, you kind of send a hint message to the coding parity OSDs saying, start reading the data, we're going to send you a delta to apply in a moment. That then means that the reads of the coding parities can happen in parallel with the read of the data. And so that way we won't increase latency, but we are reducing network bandwidth. So we're still sending the write to the primary OSD, and so we've still got that kind of zigzag there. Obviously, we can improve things further by having the client work out which OSD it needs to update and send the write directly to the OSD that needs to do the update. And so that's a kind of further reduction in network bandwidth. At this point, we're getting pretty close to the performance you'll get with a replicated pool. In terms of network bandwidth, comes in, 2 copies being sent across to the coding parities. That's same amount of network bandwidth as if you were using a replicated pool. We are doing 3 reads and 3 writes. In comparison, a replica 3 pool would just be doing the 3 writes, but those 3 writes still actually involve doing metadata reads. So it's not twice as bad. That's probably getting to the point where your performance is going to be good enough. One of the challenges of sending writes directly to the OSD is kind of coordinating things. So with reads, it's fairly easy. You can send reads, the OSD's got the data, all it's got to do is read it and send it back. With writes, things get more complicated, in particular if there's multiple writes happening, or if we have to do recovery or backfill or something like that to the object before we can process the write. At the moment, by sending it to the primary OSD, it's a kind of centralized point in processing all of the writes to that object. It can kind of make sure that all of those housekeeping activities occur. If there's multiple writes happening, the primary can do the serialization and make sure that they're applied in a consistent order. Because what we don't want to do is have two writes occur and for the updates to the coding parities to occur in different orders for the two writes, because that could end up causing inconsistencies between the parity codings and the data. So we need something to put a bit of ordering. So this is possible, but we probably need some extra control path messages to the primary OSD to still have a centralized point of control to do some of the ordering, at least in some of the more unusual scenarios. Maybe for some of the good path normal cases, we can get away without some of those control path messages. Choice of chunk size. So currently, when you use Erasure coding, the default chunk size is 4K. And so that means, even with all of these optimizations, if I do a 16K read, not a particularly large read in the grand scheme of things, then it gets split up into 4K chunks, and I have to go and read it from 4 different OSDs. And so if I use the default chunk size, all of these optimizations will help for really short IOs, such as 4K and less than 4K, maybe provide slight benefits for 8K, but anything larger than an 8K IO, you're probably not going to see the benefits. So what do we want to do? We want to increase the chunk size. So, with an example here, if I use the 16K chunk size, then at least IOs up to 16K would all be served by just reading from a single OSD. How big a chunk size should I choose? So our thoughts here is that we probably want to choose a chunk size somewhere between 64K and probably higher, probably closer to 256K. What's the kind of rationale for choosing 256K? So firstly, let's look at HDDs. If I do read IOs to an HDD, I get maybe 200 random IOs a second to a hard disk. If I'm doing 4K IOs, if I'm doing 8K IOs, how many IOs a second do I get? I get about 200. If I do 256K IOs, how many do I get? Pretty much close to 200. Why is that? So with an HDD, the kind of time it takes to process an IO request is mainly the time it's taking the head to seek, and then the time you spend waiting for the platter to revolve round so that the portion of the disk that you actually want to read or write is underneath the head. The density of modern hard disks is so great that 256K versus 4K is a tiny fraction of a revolution of the platter, and so slightly larger IO sizes makes no difference to the performance. What about SSDs? So SSDs don't have rotation, so they don't have that problem. An 8K IO to an SSD will actually consume twice the amount of resources as a 4K IO. So if you benchmark NVMe SSDs, you might get 1 million IOPS at 4K. If you go to 8K, you'll get 500,000 IOPS. If you go to 16K, you'll get 250,000. So as the IO size increases, the number of IOPS you get decreases. So that would say, maybe I don't want such a large chunk size for SSDs, but then let's think, how much performance can Ceph actually get out of an NVMe drive. So if you have 10 NVMe drives in a server, and they can each, manage 10 million IOs a second, you're not going to get 100 million IOs a second when you run Ceph. You probably won't get 10 million IOs a second when running Ceph. So what's happening is, the CPU and the network are becoming the bottlenecks. The SSD is sitting there, idling away. If we gave it 256K IOs instead of 4K IOs, we're just making the SSD a little busier, consuming some of that idle time. So a bigger default chunk size isn't going to affect SSDs either. So to make these optimizations work, we're looking at a bigger chunk size. There does come a point, the chunk size gets big enough, there is a benefit to splitting a really large IO up and issuing two halves of the IO to different devices in parallel. That in particular, we might help reduce latency. It spreads load out. So 256K probably a reasonable place. 10 meg probably wouldn't be a good choice for a default chunk size. So there's a limit to how big we can get. But at 256K, that says most short random IOs are going to only involve one OSD being updated. There's another problem with chunk size, however, and this is probably why the default chunk size is currently 4K. And that's what happens with small-sized objects. So with a default 4K chunk size, if I do a 16K write, then I get 4 4K chunks of data stored on different OSDs. I get the 2 parities written. If I do an 8K write, what the code actually does today is it will write 4K to the first 2 data devices. It will put padding, so it actually writes data. It actually creates zeros, sends them across the network, writes them to the drive, consuming capacity on your drives. So you get padding on data 3 and data 4, and you get the coding parities. And so that says if you create small-sized objects, so let's say I just created a 4K object, then that would actually consume 24K of capacity on a 4+2 Erasure coding. That's a 500% overhead. If I had a 10+2 Erasure coding, then the overheads are going to be even worse. And so, this is a problem with Erasure coding today. Those of you using object storage with really small object sizes, might be aware of this effect and the fact that the capacity overheads for storing those small objects can become quite large. If we increase the default chunk size, so here we go with our 16K chunk size, a 16K write has now got 16K of padding on 3 data drives and the 2 Erasure coding parities. And so you can see, for just a small 4K write, we're up to 2,300% overheads for storing that 4K object. I don't think anyone thinks that's an acceptable overhead. If I chose a 256K default chunk size, obviously the problem's going to be 16 times worse. So what can we do to fix this? Well, it's really quite simple. The answer is don't bother writing the padding. And essentially we can use the fact that the object doesn't exist to deduce that there's no data there and that we can treat that area as zeros as far as calculating the coding parities. And so that then says, with my 16K chunk size, a 4K write's now only got 300% overhead, 8K and 16K write, same 300% overheads. As I get bigger than 16K, now my overheads start going down. So, that's bringing the overheads into a more acceptable range. Another advantage here is with really small objects. So let's say I wrote a 1 byte object. With the current scheme, it would take the 1 byte, it would pad it out to the 4K chunk size. And so it would be 4K on each of the datas and each of the coding parities. If we don't write the padding, we can actually write just 1 byte on the data drive and 1 byte on the coding parities. Now, okay, the object store is going to probably pad those out to 4K, but modifications and overwrites to that are then much more efficient in the object store. So another possible thought is, could we be even cleverer than just not doing the padding? What happened if we automatically choose a chunk size based on the object size? So if you're writing small sized objects, let's use a small chunk size like 4K. If you're writing larger objects, so let's say greater than a megabyte, use a 256K chunk size. So here, we're now getting our cake and eating it. When we're storing small objects, we're getting the efficiency of not consuming a lot of capacity overheads. And for larger objects, I'm getting the benefits that random access to those objects is going to give fast performance. If I look at something like librd, then it's using a default 4 megabyte object size, and so it's always going to be choosing the larger object size anyway. And so for block use cases, we'd always be doing that and getting the performance case. For files, for a file system case, if you've got lots of very small files, then you're getting the capacity optimizations. If you've got larger files, you're getting the performance optimizations. The challenge of choosing the chunk size based on the object size is, of course, objects can grow and shrink. And if an object grows, you really want to convert the chunk size. And if it shrinks, again, you want to convert it. You can do this just by reading the object and rewriting it with the new coding. If the transition point is 1 megabyte, then that says, the worst case is we've got to read a megabyte and write it back again with the different encoding format. There are actually hints when objects are created, giving you an idea what size the object is going to be. And so that way we can avoid kind of an object being created and just the initial bit of it being written. And we don't want to choose a small encoding size if the rest of the data is going to follow almost immediately. So we can use that hint to say, okay, we might only have 4K of data to store, but this object's expected to be a 4 meg object, so we'll use the larger chunk size straight away. And so that will reduce the number of cases where we have to convert the chunk size. So that kind of concludes the set of optimizations we're looking at. As I said, the partial read optimization has been done. It wasn't done by me, it was done by Radek. But I'm looking to get these other optimizations done and hopefully delivered into the main release over the course of this year. And so hopefully, by the time we get to the T release, we'll be in a much better place for being able to use Erasure coded pools for block and file as well as for object.
Any questions?
Is there a quiz?
As always. Sorry. Just coming back to the initial idea, just updating or just doing the writes from the client side. How we make sure that the data is really there and we understand which chunks have been written, just even if the client goes down. Because actually the primary OSD will tell us what really happened, and just we have a good understanding what the data redundancy is actually.
Yeah, so the right optimizations are certainly more complicated, and there's a lot more detail than is shown in these slides. There's a design document that I've written up and posted onto the mailing list. It's also as a pull request, and you can find me on on Slack, on the Ceph Slack channels, or you can find me on the mailing list as well. I can point you to that and give you more details as to how it works. Essentially, if a write hasn't been completely applied, and so we haven't managed to update all of the data and coding parities, and haven't got to the point of giving the completion back to the client, and there's a problem occurs, then the peering recovery process will actually roll back the whole write operation so that none of it is applied. And that's what happens with the existing Erasure coding implementation. With these optimizations, we'll still need to do that. There is a bit more work in the peering and recovery process to actually be able to work out what has to be undone. So that's where a little bit of the complexity is in some of these changes.
Okay, thanks.
Okay. Oh.
So as you described, the padding goes on at the moment. All those zeros. What's the pitfall of not doing that? Well, you can see none.
There shouldn't be a pitfall of not writing it.
So why is it done? I mean, obviously, it's
I
a
think,
lot of writing going on.
Yeah, so it's probably a code simplicity. The overwrites today, because they're kind of reading everything and then regenerating the coding parities, the code path today only has the use case of I've got data for every single strip and I'm creating the coding parities from it. It hasn't got special case code saying I don't need to include this strip because there's no data for it. So it's a few extra lines of code to put that optimization in is not a huge change, and there's no kind of drawback to having the objects not exist.